Good morning. Thank you for the invitation to this really nice forum. In this study, we tested the influence of 3 different tartaric stabilization treatments on wine aroma. For that objective, we carry out several analytical procedures to obtain a detailed information of volatile chemical composition of the wines. And after that, we treat the data, and today I would like to show you that this is not going. Okay. And today I would like to show you this data. But first, the experimental setup. You can see here that I don't know. Sorry, I don't know why it's moving without my
the mouse?
permission. Where is the mouse? Okay. It seems like it's still. Okay, I think it's now working. Okay, I said the experimental setup of the experiment. Come on. I don't know. I don't know why it's working like this. Because sorry, I don't touch anything and it's moving. Okay, this is, come on. I'm going to do it fast to be on time with this. Okay, the experimental setup, we divided a Cabernet Sauvignon wine in 3 batches. One batch was subjected to 7 days cold stabilization, the classic cold stabilization. Another one was added with 10 grams per hectoliter of potassium polyaspartate and 40 milliliters of Arabic gum. And the final batch, the third part, was added with CNC and 200 milliliters per hectoliter of Arabic gum. The same setup for the Sauvignon Blanc, but in this case without the Arabic gum. Okay, and with this, after these treatments, we analyzed the wines, and we use several analyses depending on the concentration and the type of volatile that we were analyzing. And these different methods depend on this concentration. And for example, for a compound that, a family of compounds that is important for the aroma of Sauvignon wines, like alkyl methoxypyrazines, we use a method based on a stir bar covered with a sorbent. This sorbent extracts the compounds, and after the extraction, we thermally dissolve the compound into a multidimensional gas chromatograph coupled to mass spectrometry, and from there we obtain qualitative and quantitative information. Okay, so with this, with all these analytical methods, we obtain this concentration data for 70 compounds. And you can imagine that these compounds range in a lot of concentration, and you can see here that compounds in wine, volatile compounds in wine, cover 10 ranges of magnitude in concentration, from compounds like ethanol, that is in grams per liter, to compounds that are in the range of nanograms per liter, like such as methoxypyrazines that I commented before. The important thing here is, as you know, is that a compound is not more important for the aroma of wine because it is in a higher concentration. You know, we have to take into account its odor threshold in the wine so that we can understand its role. So let me remind you the concept of odor aroma value. Odor aroma value, or OAV, is defined as the ratio between the concentration of the molecule that we obtain by these analytical methods I told you before, and the olfactory threshold of that molecule in wine. So if the ratio is equal to 1 or above, the molecule will be active in the wine, and if it's below that 1, if it is below 1, it will not be perceived in wine. So, of course, you know, this is an oversimplification because our perception of the wine is far more complicated than this, but it could be an acceptable approach to process the data. So instead of showing you today the raw data, all the concentrations in a table, we group the chemical families and we assign to them its principal vector of aroma or aroma node. So the 16 esters that we analyze, we can say that they are responsible for the fruity aroma. 8 higher alcohols quantified, responsible for the herbaceous or fusel aroma. 4 carbonyls that we can relate with lactic aroma. 8 seeds or terpenes, cinnamates or norisoprenoids related with citric or floral notes. Phenols that are related with leathery or spicy aromas. Lactones, including whiskey lactone, vanillin derivatives, and of course, the alkyl methoxypyrazines responsible for this off flavor of bell pepper that we can find in some Cabernet Sauvignon. Okay, so let me show you the data. So in this figure, we have the sum of all the odor values that were above 1, grouped by chemical families, and expressed as a percentage. And this is the results for the red wine stabilized with cold treatment. And you can see that as we can expect from a young red wine, it was dominated by fruity aroma, lactic notes, and herbaceous, and some other minor notes. But the important thing here is if we compare this with the results from the potassium polyaspartate treated wine stabilized with potassium polyaspartate or with the CNC wine, is that you can only appreciate in the sum of all the families only only minor differences. And I can tell you that these differences were not significant from a statistical point of view. And of course, they were not significant from a sensory point of view. In the case of the white wines, same approach. In this case, fruity aroma was more dominant. Together with the herbaceous notes, it will account for more than 90% of the aroma. But again, if we compare the cold treatment with the wine with potassium polyaspartate and the one with CNC, you can see that practically the differences are really small. And again, no significant differences from a statistical or sensory point of view. And this is in agreement, is in agreement with the data that Paula has shown before. And of course, it's in agreement with all the data we obtained in the Stabby Wine project. So, in conclusion, from this data and the data that we obtained before, we can say that the tartrate stabilization with potassium polyaspartate did not alter wine aroma composition when compared with cold treatment or CNC treatment. And to end my presentation, I would like to thank all the people in our lab in Zaragoza, of course to Enartis for its financial support, and especially to you, thank you for your attention.